Hi, everybody, and we're going to talk a little bit about kind of some concept mapping with the carbonyl reactions that we're talking about with strong nucleophiles. We're going to have to do this again when we talk about weak nucleophiles, but for right now, we've just got really strong carbon or hydride nucleophiles that we're going to be working with. So I have all of the different electrophiles that we might run across. I guess I didn't put epoxides on here, but all the carbonyl electrophiles that we might run across here. And I'll try to put the epoxides at the end when we get there, so that we can kind of see what happens with the different carbonyls and the different reagents that we might run across. So there are a few kind of special ones on here that we're going to talk a little bit about. But first, I want to talk about the reactivity of the actual nucleophiles themselves. So for nucleophile reactivity, we are looking at lithium aluminum hydride being the strongest nucleophile. Okay, that's going to be the most reactive. The second most is going to be the organolithium. Then we're going to have Grignard. And then we're going to have sodium borohydride. Okay, so we'll see as we go in lower reactivity nucleophiles and lower reactivity electrophiles, then we will start to see no reactions being possible. So the way that I've organized the carbonyls here, I did it as best I could in terms of carbonyl reactivity. So we have the most reactive carbonyls up here. And then down here where we've got way at the bottom amides, we've got the least reactive carbonyls. Okay, so I kind of did it on a y-axis type of situation as well. Okay, so as we think about those things, we're going to start to see some of those trends become apparent. So when we've got, a really cranking high activity electrophile, pretty much everything's going to react with it, which is exactly what we see with an acid chloride. So just like we saw in class the other day, we're going to end up getting two equivalents of whatever nucleophile you're using because we've got that chlorine leaving group. Okay, so these will all have the same mechanism. It's that kind of substitution addition mechanism. Right, so we'll have, should have made space for drawing mechanisms out here. Oh, I regret things right now. Oh goodness. Okay, we add to the carbonyl carbon. We can reform that carbonyl. So now we're at a ketone, and then we can come in again to make the final double addition. Okay, so we're going to end up getting, once we do a acid quench and everything, 2 of our R groups added on, and we still have the original R group left over. Okay, so we're going to end up getting a tertiary alcohol out of this. If you use sodium borohydride or lithium aluminum hydride, the only difference there is that instead of R's, you're adding H's. So you're just changing your nucleophile from a carbon to a hydride. So you're going to end up with an H. H. Actually, I'll put it on the other side. Prime H. Okay, so we end up with a primary alcohol. And that's for both sodium borohydride and lithium aluminum hydride, same thing. All right, so if we go down to the next one, so this is a special aldehyde. This is formaldehyde, so you've probably heard that word before, maybe in biology class, talking about preservation and stuff like that. So that is the structure of formaldehyde. So it's a very reactive aldehyde because it doesn't have any steric hindrance on either side. So it's very, very open for attack. So that makes it really electrophilic. And aldehydes are generally more electrophilic than ketones anyways, because of that steric business. But because we don't have anything on either side, it's really, really good. So in this case, if we add in our Grignard or our organolithium or one of our hydrides, we're doing a single addition. So this is simply an addition to a carbonyl. Okay, so up here, we do end up having a substitution at one point where we're substituting an R group or an H for a chlorine. And then we do another addition reaction. So it's a substitution, then addition. Down here, we're only going to end up seeing one addition because we don't have any good leaving groups here. We're not going to see an H minus leaving group or a C minus leaving group. Okay, so we can end up getting a primary alcohol here, or we can get methanol essentially. So I would just label these as not really useful. There is nobody that would make formaldehyde into methanol because they needed to use methanol. The only reason that he would do that is like if the world just stopped and the only thing you had is formaldehyde, but you needed methanol. But you would just buy methanol. So you can make methanol out of this, but it is not a practical reaction. Okay. So we'll just make a note. All right. That was a really big space. Okay. On to the next one. So the next one is just a generic aldehyde, anything that has that aldehyde functional group. It's going to be pretty much the same thing, right? So we're going to end up having Grignard or organolithium or hydride attacking there, moving electrons up, and then we get right to our quench. Okay, so that one we can make a secondary alcohol. If I add a hydride, then I'm going to end up getting a primary alcohol out. Okay, if we move on to carbon dioxide, again, this is a special one. It's not a generic. There's only one way to draw carbon dioxide, and that's that. So in this case, it's a little bit different than what we've seen so far. But think about it from this perspective. It is a carbonyl. It just has kind of an extra on it. But when we're using this, we're really going to see it act kind of as one carbonyl-ish. But this is a situation where we're going to start to see some differences between the organolithium and the Grignard reactions, which is why I have them separated out. Again, for the situation with sodium borohydride and lithium hydride, just like in the formaldehyde case, we are again in not useful territory. So it's either going to make formaldehyde or it's going to make formic acid or something that's just not very helpful. So this is going to be labeled as a not useful product. So this is something we don't really need to consider doing because there's no point in doing it. So for carbon dioxide, if we add a Grignard to it, so let's do down here. So if I've got MGBR, so I can just attack that like a regular electrophile, a regular carbonyl. We're going to go here, push electrons up onto one of the oxygens. So what that gets me is a carboxylate anion, okay? So then we need to think, think about like acid chlorides. I can still react once I have a carbonyl left, right? And I still have a carbonyl here. The problem is Grignards are not strong enough to attack carboxylate anions. So we go straight to the quench. Okay, because we hit an unreactive part, so we're going to be stuck right here. So this product is a carboxylic acid, which is kind of cool because it's another way that we can make carboxylic acids that we did not have before. And it's a really fun reaction to actually run because you literally just drop dry ice in with your Grignard reagent. It's really cool. So tons of fun. Anyway, so let's go on to the organolithium. Okay, so the first part is going to be very similar here. Okay, so we're going to have our organolithium come and attack our carbon dioxide, make our carboxylate anion, and this is when we start to see the differences. So the carboxylate anion is not a very good electrophile. So if you look at my list, it's way down here. Okay, it is just above amides. So it's a pretty weak electrophile. The reason for that is because it's got so much electron density in it already, right? So we can imagine the resonance structure here where we've got a negative charge on both oxygens. And so that's a lot of electron density to be sitting right around that electrophilic carbon. So it makes it not very electrophilic. So you really need to have a really strong nucleophile in order to get it to react. But organolithiums are those strong electrophiles. So what we can see is we can have another equivalent of organolithium come in, and we're actually going to make the 2- structure, which is why you need this to be so strong, because this is what we get as an intermediate. So we get double addition. At this point, we cannot do anything else, right? Until we have a proton source, we are just stuck here. But once we get a proton source, we can end up forming the diol. And we've actually seen before during the chromic acid mechanism that the diol is in equilibrium with the carbonyl, right? So let me do this. Okay, so the equilibrium is going to favor that carbonyl compound. And we're actually going to see a symmetric ketone formed. Okay, the only reason that we end up with a ketone here is that once you add that acid there, it's going to first react with any of the alkyl or the organolithium that you have left. So if you've got any excess, these two things are going to react together, neutralizing, quenching the organolithium. So then it gets protonated, it can't do anything else. And then that's when we see our ketone get formed. So it's not that the ketone is forming while this is still around. This is going to quench the RLI here. So it's going to be unreactive. So that we can actually scoop up that ketone. Alrighty. And if you want to review that mechanism, definitely come talk about it. And we will be doing more of these types of mechanisms pretty soon. Alrighty. So on to ketones, okay? Ketones, again, they're going to be very similar to aldehydes, right? So we're going to have a single addition of our carbon or hydride nucleophile. That's going to get us to a tertiary alcohol. If I use a hydride, that's going to get a secondary alcohol out. Okay, and that's going to be the same for organolithium and Grignard and sodium borohydride and lithium hydride. No difference there. All right, so then if we come to carboxylic acids, so if you notice what I've done, I have one that's carboxylic acid and one that is carboxylate. Okay, the reason for that is that all of these have the same first step. Okay, they are all going to react with a carboxylic acid in the same way, in that we are immediately going to get a deprotonation. Okay, so the only reaction that they do with a carboxylic acid group particularly is an acid base. Okay, so they are going to give you the same thing no matter what nucleophile you're using. So the differences come in when we start talking about what happens to the carboxylate anion afterwards. So if you've got a carboxylic acid, this is where you're going first, no matter what. Then can we do anything with this one? Okay. So in the case of sodium borohydride and magnesium and the Grignard, the answer is no. We don't have anything, no reaction. Okay, because what we're essentially seeing is, if we remember our reactivity list, these two are the lowest reactivity, and we're getting to a low reactivity electrophile. So once we start getting down here, it's not enough. It has to be up here. And we do see reaction with the lithium aluminum hydride and the organolithium reagent. Okay, so if I have the organolithium, we already saw what we could see happening here, right, where we end up with a ketone. In this case, we can get a non-symmetric ketone because we are already starting with an R group on our carboxylic acid. So same process as with the carbon dioxide. We've got the R1. We're going to make a ketone and add in our other R group. Okay. For lithium aluminum hydride, it's going to be a little bit of an interesting mechanism. I'll probably do a separate video with the LAH mechanism for carboxylates and amides separate, just because they're a little more complicated. I'm not going to expect you to know them, but I know a lot of you want to know about the mechanism, so I will probably make a separate video for that one. But at the end of the day, you're doing two additions of lithium aluminum of the hydride. So you're actually going to end up getting a primary alcohol out. Okay, so it's going to be fully reduced, and it's because we have essentially a Lewis acid present, we can get away with kind of kicking off some stuff to make it so that we only have one oxygen left, where we don't really have that as much in the organolithium case. All right. And we're on to our final one. So the amide is the least reactive of them all. So there's going to be no reaction for a lot of these things. So there's no reaction here. There is, oh my goodness. I forgot esters. Oh no. Okay. I'm going to finish amides. I'm going to pause it and then I'm going to put esters in. All right. So there's going to be no reaction for Grignards. And so for this class, I'm going to say no reaction for organolithiums. It's not entirely true. And there are some amides that are actually quite reactive, that are kind of specialized ones. They're a little outside the scope of the class though. So when we're looking at amides, we're going to say that carbon nucleophiles do not go with them, because they are quite poor electrophiles, because we've got so much electron density donated in from that nitrogen. So we're going to say no reaction here. And your book makes zero mention of it at all. So we're going to keep it with no reaction for those. The only one that it does react with really, really reliably is lithium aluminum hydride, which is the top of that reactivity totem pole, right? So again, we're going to see a situation where we're going to lose our carbonyl completely. And this is actually going to get us to an amine. Okay, so this is, I guess, the first way that we know how to make amines, I believe. Well, that's not true. We know how to reduce nitro groups. I guess we've got that. Okay, so we go all the way to the amine. So you can make primary amines, tertiary amines, secondary amines, any kind of amine that you want. All right, I'm going to pause this real quick and get the esters in here. Okay, we're back with esters. All right, so the ester is going to go underneath the carboxylic acid, but in front of the carboxylate anion. Okay, so the reason for that is just that it's really easy to deprotonate something, a little harder to do nucleophilic attack. So that's really it. These two things are very, very similar in terms of like carbonyl reactivity. The problem is that is just a little bit more reactive than either of the two carbonyls at this point. So that's why we see acid base up here, and then we're going to get to the esters right afterwards. Okay, so we talked in class a little bit about how we go through that mechanism. It's the same exact thing as the chloride mechanism, right? So we're going to start by seeing the organolithium or the hydride or the Grignard. Going to the carbonyl, we end up with our tetrahedral intermediate, and this is R2, R1, there we go. Then from here, just like we did with the acid chloride, we can push those electrons down to make another carbonyl, kick off that leaving group. We get to a ketone intermediate. That ketone is still reactive. We've seen the ketones up above. They've already reacted. So we bring in again and we get to a tertiary alcohol, okay? So that's what we're going to get over here, just the protonated form of that. Okay, and notice that this R2 that was on the oxygen, we lost it. It's going to show up as an alcohol over here on the other side. So we're essentially getting two alcohol products out. Okay, depending on what you want to keep, maybe you want that other alcohol, maybe you don't, it's fine. So for lithium aluminum hydride, we're going to see the exact same thing. We're just adding two hydrides, because if the Grignard did it, the LAH definitely can. So we're going to see a similar situation here where we're going to get a primary alcohol plus that other alcohol as the leaving group. Okay, and then we're left with our lowest energy nucleophile. Sodium borohydride is not going to reduce esters. Okay, so it's a nice little thing in terms of selectivity. So if you have an ester that you don't want to reduce, but you've got a ketone that you do, use sodium borohydride. Then you'll keep the ester but reduce the ketone. So it's nice to be able to play with those things, but no reaction for the sodium borohydride version. Okay, so I think that's about all of them. Have an excellent day and let me know if you have any questions.